Good afternoon. Let's continue talking about particles and quasiparticles in crystal structure. Now you're definitely sure that electron is a particle and also a wave. But if we are talking about electrons situated in the periodic crystal structure, is it really still a particle? Is it still that electrons that are free in the vacuum? Let's think. Electron situated in the periodic potential possesses its ordinary charge, its ordinary spin, but instead of the rest mass of the electron, it has the effective mass that are dependent on the energy, on the wave number, and so on and so forth. And instead of momentum, electron has a quasi-momentum. So, half of its characteristics changed compared with the free electron in the vacuum. But what about quasiparticle? What features does it have? Quasiparticle is characterized by energy, and it's not constant. It has quasi-momentum and effective mass. An energetic spectrum describes its motion. Its charge is only the constant of coupling. I think that there are a lot of similarities between electron and a quasiparticle. So, it means that an electron situated in a periodical crystal structure is not a particle anymore, but a quasiparticle. So, what do we have in a crystal structure? We have a complicated, many-body system with a lot of interacting particles. And we can simplify it by using not many interacting particles, but a small number of non-interacting quasiparticles. In this case, quasiparticles will be viewed as elementary excitations of the system consisting of many real particles. Another well-known quasiparticle is the Hall. We all know that Hall is like the absence of the electron, and indeed, the Hall describes the ensemble of electrons in the valence band from which one electron has been removed. It also can be viewed as a void in air or water to which we can apply notions like size, speed, and acceleration. So, what features does it have? It has the charge that is opposite to the electron. It has the effective mass that depends on the shape of the valence band. It has the spin the same as the electron, and its kinetic energy is rising from the top of the valence band downward, so it's the opposite situation to the electron. So we see that Hall really has a lot of features as a quasiparticle. Do you remember when I showed you the band structure of real semiconductors? You saw that in the region of the valence band there were usually several different energy branches. In this case, there are 3 of them. So all these 3 energy branches are connected with different holes that have different masses. So, up to this point, we were considering that electron and the hole are quasiparticles, but they behave independently from each other. But I think you realize that it's not really true, because, the hole and then the appearance of the hole is fully dependent on the electron motion. So, if we have such a situation when the concentration of electron and holes increases, they can form electron-hole pair. How can this happen? First of all, we have a transition of the electron from the valence band to the conduction band. Instead of the electron in the valence band, the hole appears. Also, this process can be occurred with the help of the photon. In this case, these equations will describe it. So, we still have the band gap energy. It means that only photons with the energy that is equal or more than band gap energy can be absorbed. So band gap energy value defines the spectral location of the optical absorption edge, after which the absorption spectrum becomes continuous. If the energy of the photon is equal to the band gap energy, then electron and hole will have zero kinetic energy. It means that band gap energy equals to the minimal energy for creation of the single pair of free charge carriers, an electron and a hole. But if the energy of the photon is more than band gap energy, so the excess energy breaks into the kinetic energy of the electron and the kinetic energy of the hole. But we should remember that the photon momentum is really very small, so that's why on this band structure the arrow of the transition is almost vertical. But how does this happen? Then the photon with very little momentum produce two quasiparticles with two big momentums. If we look at the vectorial sum, we will see that this can be realized only when electron and hole move in nearly opposite directions, and the vectorial sum of their momentums will fit the small value of the momentum of the photon. We also see on the band structure that not only upward transition can be realized, but also downward transition. This transition describes the recombination process of the electron-hole pair. It means that electron-hole pair converts into the photon, but with another energy. If we consider the case of indirect gap semiconductor, we see that the bottom of the conduction band and the top of the valence band are situated at different wave numbers, so the transition number 1 is prohibited. Instead of the one-step transition, we should go through at least two-step transitions via number 2 and number 3. To realize this situation, we need more energy and more momentum, and the lack of the momentum can be taken from crystal lattice by absorbing not only photon, but several phonons. Because of the involving several quasiparticles in this process, its probability is really very little. Because of this, the absorption of this system or of this material is also very little at these energies, unless the photon which has the energy that enables the direct transition, number 4, is allowed. The recombination process in such system also has very little probability.